Welcome to Study Loop.
In question 42 of chapter 22, what we're looking to find is the chemical formula, as well as the group 6A element and its oxidation state for all of these compounds that you see over here. So to first orient ourselves, let's just consider a little figure taken from the textbook that shows that the group 6A is the third column from the right on the periodic table. And what that means is that the possible oxidation states for these compounds can go from -2 if we add 2 electrons to achieve an octet, a noble gas configuration, all the way up to +6. So, for these problems, I'm going to be emphasizing the non-oxygen elements. Oxygen is in group 6A, but in this chapter's organizational setup, it's sort of got its own section in this part of the chapter. So we'll be focusing on the non-oxygen elements when we say our group 6A element. But let's get started. So for this first one, we have sulfur tetrachloride. Judging by the name, we've got sulfur, and it's tetrachloride, which means that there's chlorine, and there are 4 of them. So we have here a covalent compound, which means that its chemical formula is not determined by charge balance, so just sulfur tetrachloride based on the naming scheme. So our group 6A element here is going to be sulfur, and chloride is going to, based on the name, chloride means Cl-1, or I guess in proper notation, it'd be a Cl1-. And there are 4 of them. So to maintain charge balance in this compound, this guy needs to be in the +4 oxidation state. All right, so that's sulfur 4+ as our group 6A element and its oxidation state. Moving on to part B, we've got selenium trioxide. So we've got a selenium. And again, this is a covalent compound, so that means it's just selenium. We don't need more than 1 to maintain charge balance, for example. So it's trioxide, which means oxygen, and there are 3. In terms of assigning oxidation states, oxygen is very nearly the highest priority in most every case. And so what that means for this problem is that oxygen is going to be -2. And there are 3 of them. So for this compound to be charge balanced, this selenium needs to be in the +6 oxidation state. Moving on, we got sodium thiosulfate. This one is an ionic compound because thiosulfate is sort of its own beast. So to address that, we're actually going to bring in another handy-dandy figure from the chapter, which is figure 22.19. So if we look at this structure, we've got a sulfate here on the left and a thiosulfate here on the right. Both of them have a total charge of -2. But let's go through this and assign oxidation states. So if we look at this one on the left, oxygen is going to be the highest priority, which means that these oxygens are all going to be -2. So in order to have a total charge add up to 2- for this whole thing, This sulfur must be in the +6 oxidation state. If we do the same thing on the right, you get -2 for all of these. These sulfurs then are going to have to be +2 each. So our sodium thiosulfate then has, again, this is an ionic compound based on the name, because we're just given a cation and anion name. There's no prefixes. So that means that sodium thiosulfate is going to be a thiosulfate, which we know from this figure is S2O3 and has a charge of -2, which means that we need 2 sodium counterions. Now we have sulfur in, as we've shown over here, the +2 oxidation state, and oxygen in the -2. I'm actually going to skip to E because we just talked about this figure. Sulfuric acid is just a sulfate with hydrogens as the counterions. So that means we've got our SO4 -2 charge. So to counter that, we need 2 sodiums, or excuse me, 2 hydrogens. And the sulfur will be in the +6 oxidation state. All right, now let's move on to part D. Hydrogen sulfide. So for hydrogen sulfide, this is also an ionic compound because there are no prefixes or suffixes. So that means we have sulfide, which is sulfur in the -2 oxidation state, and we'll need 2 hydrogen cations to counterbalance that. So sulfide is sulfur, by definition, is a sulfur in the 2- oxidation state. All right, if we can move on to F, we have sulfur dioxide. Again, this is a covalent compound, like in part A, and you know that because you see this prefix here. So sulfur dioxide. Sulfur is lower in priority than oxygen. So oxygen then has its oxidation state assigned to 2- based on our rules for assigning oxidation states. There are 2 of them, which means that the sulfur must be in +4 oxidation state to maintain charge balance. And lastly, we have mercury telluride. This is going to be an ionic compound, and mercury is generally in the +2 form. So we've got mercury and telluride. Telluride will also be in the -2. So the ionic compound notation for these two will just be HgTe. So we've got our telluride here, which is just tellurium -2, and the mercury counterion. And that's it for this problem.